So our final speaker is Pedro Gusmão. He is also at Cambridge, but he's going to be presenting quite a different type of contribution. And this is not vertical FL, but simulated FL. If you're doing a simulated FL, it's a really important step in the development of any FL solution. You come up with the idea, you know what you want to try to federate, but at some point you need to start looking at the parameterizations of it. What happens if I have more nodes? What happens if I have more data? How is it going to work at scale? And without the simulator piece of this, it's never going to happen. And if the simulator is not fast enough, you're never going to do it. And so Pedro and a bunch of folks there have come up with some really interesting ideas about how you can simulate things much more efficiently with nice, high, fast throughput. You can trial and error to your heart's content until you nail that solution, and then you can deploy. So I'm going to hand over to him. He can tell us about how they've done it, how they've managed to beat, I think, every other framework they could find, building on top of Flower and introducing some really powerful new ideas. So over to you, Pedro. Thank you for coming today.
Thanks, Nick. Thanks for the introduction. Just checking, can everyone see my screen?
Yes, we can see the slides.
Perfect. Yeah, so again, thanks for having me. Hello, everyone. Today, I'd like to talk to you about high-performance simulation in FL. This is actually part of the work we submitted recently to MobiCom. And obviously, there's a group effort with all the people who participated being shown here. So I guess just to start with this presentation, I think it's important to know why are we doing this, right? So why is FL simulation important? So it is important because it helps you understand the effect of training using a large amount of data that is distributed over many clients. It helps you test a few ideas that you have. For example, if you have a new idea around a new type of aggregation strategy, maybe you have an idea on how to create a model that is by nature distributed, and you want to test this idea. And maybe with these ideas, what you really are trying to do is to close the existing gap between centralized training and federated learning. So we know that from reading papers in federated learning, sometimes people will report their results on centralized training, and this is usually better performant when you compare it to federated learning. And that leads us to a kind of ultimate question that at least I want to answer, which is, can data availability, meaning with all the data that you can unlock with federated learning, could we possibly beat the convenience of being able to train everything centralized? Could we actually outperform centralized learning? But obviously, we want to do this within reasonable time. Our experiments, they should finish at least within our deadlines, right? So we want to run simulations and we want to have reliable results, but we also want these results to deliver within a reasonable time, so that if you have shorter experiments and you get quicker results, you can run more experiments, try new ideas, so on and so forth. So just to give you an idea of what FL simulation is in a nutshell, well, we all know that in the regular federated scenario, you have a federated learning server that will sample clients, and these clients will train in a federated way. When you're doing simulation, what you do is you still sample those clients. Maybe you sample client IDs, and then you have a group of nodes, of processing nodes. Each of these nodes are servers having multiple GPUs, and you want to allocate these clients, these virtual clients, as also Flower uses, to these different nodes, and hope that they will train those clients, again, in reasonable time, give you back their trained model. You aggregate in your your server, and then you continue performing the round. So the simulation is very similar to the real thing, just except that sometimes you do not have enough resources to start a single process for each one of your possibly thousands of clients that you're sampling. So what you do is you sample IDs, you send these IDs to individual nodes. These nodes might contain a concept of a worker. A worker is nothing but a process that will execute the training of multiple virtual clients. It can run one worker per GPU. That would possibly not be very efficient. We'll see why. But then you can also run multiple workers on the same GPU, simulating multiple clients running on the same device. Okay, so this is just an overview. You have the server, sends IDs to different nodes. The different nodes will assign these IDs to different workers. They will train, they will respond to the server. Now, if we see this process as a general machine learning workload, we might be biased towards some requirements, some characteristics that are actually from centralized training, centralized learning. And when we look into centralized learning, we see that usually you have large and homogeneous workloads. If you think about large language models, you usually have very large workloads that have to be distributed over multiple GPUs, and that the training process of running those large models of learning, of training very heavy workloads, they probably run across days and even weeks, depending on the model. This is not what happens in federated learning. When you use federated learning, you usually, again, if we think about cross-device, you are planning on training models on mobile phones. So a mobile phone will not have a GPU or CPU that's comparable to a powerful server with multiple NVIDIA GPUs. So you're training on very small heterogeneous workloads, because now you're training over different clients. Each client will have different amounts of data. You will have shorter training processes. Imagine now that you want what you would possibly train in a few seconds in a mobile CPU. Now, if you're really training in a simulation environment using server GPUs, that will take fractional seconds. So the workload for a single client is very, very short. And since it's very short, like we mentioned before, the concept of worker, it is possibly better to have multiple workers, multiple virtual clients running on the same GPU. This is because each client will only use a single fraction of a GPU. And here what I have are two plots that demonstrate exact that. On your left, you have the distribution of mini batches over the clients. So you have clients, the number of clients that will have a specific fraction of samples for that data set. We have here three data sets: open image, which, as the name implies, is made of images for image recognition. You have Google Speech, which is a keyword spotting data set. And you have Shakespeare, which is usually used for language modeling. And as you can see from the slides, you have peaks at different points of this distribution, meaning that you do not have a kind of constant load per client. You would like to have one peak on only one position of these for each one of these distributions. That means that each client would have the same amount of workload, and that's really easy to work with. On the plot on the right, what you have is the training time distribution of these clients over heterogeneous hardware. So in a real scenario, in a real research scenario, what you do have is you have nodes, but not necessarily they have the same GPUs. So if you do assign similar clients to different GPUs, they will train in at different speeds. Okay, and it will end up that you will probably have one GPU that's idle whilst another one is still working, just because it's slightly slower. And that is actually the regular way that federated learning frameworks in general work. They use what is called a naive pool-based approach to client sampling. So in this kind of approach, in this pool-based approach, you have the server that, again, samples clients, but then it creates a queue of clients where each node will sample a client and perform its training locally. And once it's done, it will sample another client from this queue, one at a time. So as soon as it's done, it will sample another one and train again. Okay, this kind of sounds efficient, but unfortunately it's actually not. So the issues with this are that fetching new clients every time you finish one will incur into more communication server node per round. GPUs, by doing it this way, will probably not be fully utilized. So you have GPUs with a lot of free memory, especially when they're done with one client and still waiting for the communication. And also, by allowing GPUs and workers and nodes to each one sample from this queue, you basically are allowing hardware to be treated equally. And that's not good, again, because you can end up sampling a very large client to a worker that is not very fast. And this, in the end, will hold up your round. You will hold up the end of your round by submitting the training model. You still have some GPUs that are just idle. Another approach, and this is the approach that we take in our submission, is this push-based approach, where the server will predefine which clients will run where. And in addition, it will allow also the nodes to perform a kind of partial aggregation, meaning that if your aggregation strategy, like federated averaging, allows you for associative property, then you can actually pre-accumulate, pre-aggregate the partial results from your workers before you send this back to the server. So this is the approach that we do, that we take in our paper. But again, the question is now, how do we associate clients with hardware? How do we choose where to send what? And I think every time we have something like to remember, it's good to have a meme. So what we really want at the end of the day is to have balanced workloads across heterogeneous hardware, so that all workers will finish simultaneously. So if they all finish simultaneously, so no one's idle, you're done, you can submit your partially aggregated models, and you can start a new round. And how do we do it? Well, eventually I will show it, but it's by using client placement based on the training time. So we will eventually evaluate the training time that each client takes, and then based on this, place this client onto the right piece of hardware. Here's the implementation that we do. We call it Pollen, kind of related with Flower. And obviously we use Flower because we all know how to use it. It's very easy to use, it's very easy to modify. So we simply create new models that can be easily integrated with the framework. And the main ones that we created here are the resource allocator, the placement strategy, and the partial aggregation. We also create a new kind of client that we call it now worker, that is able to take a list of virtual clients and process each one of those. But again, this is almost trivial with Flower. So going to the resource allocator, as I said, it is important for this process for us to know what kind of hardware we have, especially when we have different kind of hardware. So we do have this concept of resource allocator and a node resource module that will communicate and the number of CPU cores, the number of GPUs that are available in each node to the server, so that the server can make a decision on which hardware is faster, which hardware is slower, so on and so forth. With this information, we use the concept of placement strategy. And this placement strategy, what it does is it will associate, based on the information that we receive from the resource allocation, it will associate a specific client with specific characteristics. For example, the data set size onto a specific worker. Okay. Again, the whole goal here is to have balanced workloads so that everyone finish at the same time and you don't have idle hardware. And you can see from this slide is that we still have the list of clients that we want to train, but then we make this decision and send a subset of this list to different workers. Okay, so here we have 3 workers in this example. And finally, to make things even faster, we perform partial aggregation inside the worker and inside the node before we can set it back to the Flower server. Now, we studied different kinds of placement strategies. I briefly mentioned the one based on time, but we also compared to different kind of placement strategies. Here we have the naive random robin, which is very basic. What you do is you have that original list, and then you keep sending them across all your possible devices. Then you have a better version of this, which is the sorted round robin, where you first sort this list based on the number of mini batches that you have to train. So a client with a larger data set, the 2 first clients with the largest data set will be close together, and they will be sent to different pieces of hardware, okay, different GPUs, so that you're already trying to balance it, this training based on the data set. Then you have this batch uniform, where clients are sequentially assigned to workload, having the least amount of batches. Yeah, sorry, the previous one sorted, and this one amount of batches, yes. And finally, you have the you have the model, our proposed model, which is Pollen. And Pollen is based on calculating how much time, estimating how much time that specific client would take in each one of these GPUs, of these workers, and then assigning it to the worker where the accumulated training time would be the least. So you keep filling this kind of histogram of training times based on, okay, in this fast GPU, it will only take 5 seconds. This lower one, it will take 10 seconds. But this one is actually the current training time, total training time is very low. So we'll associate this with the slower GPU. But next time will probably be the faster GPU. So there's a we are always trying to maintain a finishing time equal amongst all the GPUs, all the workers. And the way we model this, well, there are basically 2 ways if you think about it. Basically one way, but then we take another step, a better step from this model. The basic one is that you will model the training time of a single virtual client as a linear function of its of the number of mini batches that it has. Not a number of data samples, but mini batches. This is because, again, we're using GPUs, we work in parallel. So what actually counts is the number of mini batches. We've noticed that this kind of works, but we were able to improve on this model. So we actually increment this by adding a logarithm part in this equation, which, as you can see, gives us a slightly better mean square error when we try to fit the curves based on what we we accumulated. And this is what we call in the Pollen learn-based method. And what you see here in this slide is how well this strategy does when we compare the delays between two workers. So what we are trying to see here is the minimum delta between the best and the second best workers. Again, we have the three data sets that we saw. We noticed that the Shakespeare one, all of these methods, they kind of behave the same, but this is because Shakespeare requires very few clients per round. It's a data set, it's a benchmark defined by a paper called Leaf. And you do have very few clients per round, and it just ends up that you have one client per worker. We'll get back to this very important point. You end up having just one client per worker, so it doesn't really matter that much because you have one in each queue. Anyways, you do have then Google Speech, and in Google Speech, you can see that the delta is better than even random robin. This has to do also with the distribution of the data across clients. Again, so if you have kind of kernels of concentrations of clients having very different number of data samples, that is your worst case scenario. So in Google Speech, this doesn't happen much, but when you look at Open Image, that's when you start seeing this delta between best and second best in the learn-based Pollen going down. And here, when we compare flower plus Pollen against two of the main mostly used other than flower frameworks, meaning FedScale and Flute, here's where you can see the throughput that flower plus Pollen can give you in these three data sets. So you can see here that if you use flower plus Pollen, you can have an up to 3 to 5 times increase in the throughput. So your experiment will be faster 3 to 5 times just by using a kind of smart way to assign virtual clients to different hardware. So this kind of shows why we need this time prediction and why we have to move away from that poll-based approach. But I did mention something about Shakespeare before, the fact that you would have only one client per worker. So we noticed that this learn-based approach really works very well when in real research scenarios, real simulation scenarios, which is exactly when you have a fixed setup of hardware, you have those nodes, you have those GPUs, and you want to increase the number of clients per round to a realistic large-scale scenario. That means that each worker will have a high density of clients in the end. So you won't have just one client per worker. That's not even realistic. You will have hundreds, thousands of clients in that queue. So if you can manage in great queues that are appropriate for each client, and you keep in mind that you want all of them to finish more or less at the same time, then you have probably a large concentration of clients per worker, and this is what you have in this part of the graph when you have fewer GPUs, but you keep constant the number of clients that are being used on those GPUs. So if your total number of GPUs is 2, that's where you really see a great throughput on this learn-based by Pollen. As you dilute this, as you buy more hardware, but you keep the same number of clients, you start saying that, okay, it won't matter so much. But again, this is not very realistic. You're probably not just going to buy double, triple the amount of GPUs that you have just because you want to, well, it's not realistic from a money perspective, just because you want to multiply by 10, 100, 1,000 the number participating clients per round. So final takeaway, federated learning workloads have unique requirements. Correct placement can reduce the training times, and they will. Client density matters, and we see more benefits as we increase this density of clients per round divided by the number of GPUs. And this is all I have for today. Okay. Yeah, and I'm open for questions if there are any. Thank you so much for staying this long.
Thank you, Pedro. That is bang on time. But as a consequence, we probably won't collect any questions. People can connect with you over Slack, or you got your email address there. I really love this work because what I think is really powerful about it is it's one of these situations where you look at a problem, you sort of reason from first principles to some degree, you think about what are the key drivers of the issue you want to optimize, and then you develop a system around that. And so it's a great piece of science. Thank you for sharing with us today. And it also nails down, at least advances forward appreciably, I believe, a key part of the sort of like ecosystem of tools that we need for developing these federated systems. Clearly, you need to simulate before you deploy. Definitely. And so then, and if the simulation is too long, it's going to slow down development and everything, because machine learning is such an experimental science. So thank you so much for sharing with us today. It looks like those gaps there are sort of pretty meaningful. So that's really great to see.